Everyone did anything fun? Good. Canyoneering?
Yeah, oh no, I didn't go canyoneering. We didn't get permits in time. But I went to the Grand Canyon, which was really fun.
Oh, sweet. Nice.
Yeah.
That's a beautiful place.
Does that not count as canyoneering?
I guess maybe yeah.
Chill canyoneering.
Yeah.
Nice. Okay, so today, first I want to start with projects, because now we are getting at the stage where things should be happening, hopefully. So I want to emphasize the deadline, which is for intermediate projects here. So March 23rd, and one knows which day that's going to be? Monday. Monday. I want to emphasize Monday because other deadlines were not on Monday. And you have all the way to midnight, so 11:59 p.m. for your intermediate, or however I call them, reports. So what we expect here are results, right? Ideally, there would be some results, meaning something was implemented and it's working. So that's kind of when we think about 100% for the intermediate reports, that's ideal outcome. Okay, now, you're going to submit your report, which is basically, you probably know this, but what did I call it? Project report templates. The template you have used to write your proposal, if you scroll down, you will see there is an intermediate report portion. And so the idea is that you can just continue working with the same doc. You don't need to make a whole new doc. You just continue working with it. And here there are questions you need to answer. Basically, okay, if something has changed from your proposal, here use the latest version of the proposal. If you started to run experiments and then something had dramatically, or not necessarily even dramatically, but something has changed in terms of your game plan, this is where you're going to explain what had happened. Oh, I'm sorry guys. Let me go back. And the rest of it is about the results, like share your results. If you do not have your results, you will skip this and just report what had happened, like what were you doing, and just explain what were the obstacles. This is really important. If you don't have results, we are going to base our judgment of how much work and the quality of work you have done based on that. So even if you don't have results, we can assess whether there have been just plenty of obstacles. Now, one obvious obstacle in doing research is you just keep wanting to expand the breadth instead of the depth, and that's not one of the justifications here, right? Like here, justifications would be, okay, we implemented this, but then we realize, oh, SAEs to actually train them on CHPC, we need this much memory, and this is something new to us, so we were handling these kinds of errors and learning all the way. Like that would be a good reason for maybe having trouble with training something. Okay, and here you're going to reflect on your final evaluation. So eventually we will have poster presentations, and there, as I said, in your first poster draft is when basically you have to have final results. I would encourage you here to kind of reflect how much you were able to do in a given time and how much time you have left, and then maybe revise your plan and make a solid plan and something that's achievable by the poster presentation. Now, when you submit these reports, Fatima and I are going to team teams. So every team will be teamed up with another team. And on Tuesday and Wednesday, your task will be to read a proposal and intermediate report of another team, right? So 3 pages, roughly, that you're going to read. So, how to say, another team support. And on Thursday, which is going to be then 26th, right? We are going to meet here, all of us, and we are going to have a peer review session where you are going to talk with the other team you have been teamed up with, and they are going to give you feedback. So feedback can be along the lines, okay, these things were not clear to me from your proposal, so you know, kind of a chance for you to improve your arguments, your motivation, your vision, your everything you are doing. So when the time comes to present your poster, you have a solid, confident presentation of what you're doing. And another thing here I want you to give feedback on is if you were, doing the project of the other team, maybe you have ideas of how you would approach certain methodological aspects or evaluation. You share your ideas with the other team. After, in the same session, so this is important, the deadline here will be the end of the lecture, so that's usually 12:05 p.m. You're going to submit a report of changes. Let me just make this a little bit more functional. Well, someone is on the break. Okay, what I'm trying to show is that in the same Google Doc, after the intermediate report, there is a page for here, a summary and takeaways from your project from peer feedback. This is where you're going to precisely write what was discussed. And here I want to see you reflect on the discussion. So the team might have suggested, the other team might have told you, oh, you should do this, but that might not be the best idea, and you can explain here why. Which is something we do in research very commonly. When we submit papers, we have reviewers who submit their reviews, and then there is an auto-response or a rebuttal stage where we engage in a discussion with reviewers, and maybe they have suggested something, but we deem that to be either unnecessary or would be nice to have, but you can't have every single experiment, and so on. So this is another chance to practice how we communicate with other scientists as we do research. Okay, so this is what to expect for the next week. Unfortunately, I won't be here in this session. Fatima will be here and navigate and moderate this session. Are there any questions about what to expect, what's going to happen? Any questions? Okay, if anything comes later, please send us a message and we will cover it. But just keep in mind these hours. That was a little bit unclear last time. Okay, so with that, if there are no other questions, I will continue with the actual course content. Okay, seems like we are ready for that. Okay, so we have learned a lot in this course so far, many various methods of how to approach interpretability, and maybe you have noticed that one theme across many methods was that we weren't really focusing on attention heads much, right? We were kind of fixing them and just assuming they're part of our, stack in a residual stream. However, attention heads are investigated in interpretability, especially in mechanistic interpretability. So, and that might not be surprising, right? We all know transformers, and we know that one of the key layers to transformers is the self-attention or causal attention mechanism. Does anyone want to remind everyone what attention is, just briefly, like what does it do? Emma?
It allows the different embeddings of each token to kind of take information from other tokens, I guess.
Yeah, that's right. So Emma says if you produce a given representation of a given token, this representation can be produced by a mechanism which looks into other representation of other tokens in the context and kind of picks and chooses what to mix in the representation of a token at a given position we are looking at. So our representations are becoming contextualized, right? And classic examples of when this can be useful is, for example, for disambiguating words that have multiple senses, right? Like bank can be financial bank and bank that's next to a river, and similar words. So it is an important mechanism. And researchers try to understand what is the function of these attention heads. For a moment in time, researchers have looked into heat maps that are produced. Let me write the equations. So remember, attention comes with softmax of free query heat transpose, this stability normalizer. With causal attention, we put everything in the upper diagonal to be to plus infinity here, so softmax will squish it to 0 back. And then we have the output z is of one head here. I'm going to write one head and head is going to be the AH times B, where B equals, and all of these are just the linear projections of our input, so X, W, H, and Q is X, W, K, oops, Q, H, and K, same thing. Okay, so this is a matrix of the size, I should say 0 to 1, right? Of the size of the context times the same size, where the n context is the input length in number of the methods. Okay, so I didn't want to talk much about it, but let me just find my old slides like this. Just to find some visualization. Okay, here is one visualization of A. So for some input, here he was becoming agitated. We pass it through a transformer, and for just one head, we visualize this softmax of this product, right? And this visualization can give us a heat map that looks like this. This is for birth, which has self-attention. We could look left and right. With causal attention, we would never see anything in the upper diagonal because that would be cheating, right? Okay, so we have a heat map like this, and when you observe a heat map like this, you can kind of hypothesize about what the role of this head could be. So for example, here, we can see that when we look at the word he attempts a lot to becoming agitated. And this maybe then suggests that this head maybe is capturing subject or verb relation in this sentence. Subject being he and becoming agitated, becoming a main word of this sentence. And of course, this is only on a single example, so maybe we'll pass a lot of examples and try to make sense of what the pattern could be. But then remember, you have so many attention heads, right? In just a single layer, you have dozens of them, and then you have dozens of layers, so there is a lot to investigate. And it kind of, at some point in time, it became a huge discussion of whether these kinds of attention patterns are, what is actually contributing to the prediction, right? Like when you look at this single, head and its behavior, whether that behavior is influencing the prediction. And it started with, this is a survey of this big discussion that happened in the field. It started with this paper, attention is not explanation, and then follow-up attention is not explanation. So somewhere kind of there was reasons to believe there it can contribute to prediction or not. And this is just a bunch of papers that have contributed to this large discussion. So that happened at some point of time. And what we're going to talk about today is different. It's not this kind of inspections of these heat maps. It's a different way of looking into what these attention heads are doing. So just wanted to draw your attention that at some point of time people look into these heat maps. It's kind of not a really common approach anymore. There is just so much to work with. There's just so many attention heads, and you need to pass lots of data through them, and then there are all these, confounding observations. Okay, so what we are going to talk about are we're going to return to the paper that we have talked about when we covered the residual stream, right? Like when I introduced residual stream, I mentioned this work by this set of authors from 2021, and this is where we had built our, framework for kind of mathematical framework for residual stream. So here we start with this one. And in this work, besides defining the residual stream, they're also going to look into what are attention heads doing. And this work will give us kind of math framework for attention heads. And through this framework, we are going to then do analysis of what attention heads might be doing in toy models. So analysis of toy models. And this analysis will point us into coping behavior, namely idea that attention heads some of these attention heads serve as a way to copy whatever came before in the context and predict that as a next token. Any idea where coping might be useful? Or something like coping? Looking what came before and making predictions based on that. Emma?
Since we predict the next token based on only the representation of the last token in the sequence, like it would be helpful to have information from the previous tokens
Okay.
to make that prediction.
Okay, let me repeat this to make sure I understand it. So you say coping might come handy when, if we would fully want to copy the sequence, because we can go and see what's previous and predict as the next. Or can you repeat? Maybe I didn't fully understand.
Sorry, I think I got confused by the question.
Okay, yeah, the question is a little bit very vague. Let me just set this up so it doesn't turn off, and I will repeat my question. Okay. Okay, so my question was, if I have, I have certain sequence like A, B, C, D, E, and so on, and then I come to some token, whatever, let's call it target token, and this is where I'm going to make my prediction of the next token. Why looking, when could, like in more general, I'm not looking for a specific example, rather I'm trying to see whether you can make connection with one common way we use LLMs. So again, if I'm at the target token and I'm trying to predict some next token, let's call it out, the capability to look back into the context and maybe pick and choose, maybe copy literally the same token or something similar, when does that come handy? What are the core usages of LLMs? Yeah.
Just like being a chatbot?
Just being a chatbot, right. That's a good answer. And let's just make it maybe a little bit more precise and say what chatbots are doing. Like, how do we prompt them?
Well, it's just like a message stream, so it's like if I ask it to like, say write me a poem, and I think I do a poem, and like when we get tweaked to it, it would have to go back and look at what it wrote before and then copy.
Yeah,
that
so
similar to it.
there is just a bunch of tasks where the model needs to reference the task inputs. So for example, here you gave an example of editing something that's already written, right? Like going back and seeing what's written and then, making a judgment of what comes next is a great example. Other prompts maybe include things like few demonstrations of the task, right? And we have observed repeatedly that adding few demonstrations can help models do the task better. So this is called in-context learning, or which is an example of few-shot learning. So in-context learning is when we prompt LLMs with demonstrations of a task, meaning, okay, here is an instance of task input, and this is how I would like to complete it. For example, if the task is summarization, we will give it an example of a document we want to summarize, and a summary that's actually high quality, what we would like to see here. And maybe in your own work, when you prompted LLMs, you have given similar demonstrations. Doing in-context learning is a very common way to prompt LLMs. And coping is obviously relevant then for in-context learning, right? Maybe not the explicit coping where you literally copy certain token verbatim, but the type of coping where you look back to what's happened and then you predict something similar. So the fact that this work is going to bring us to the observation that some of these attention heads are doing coping will connect us to in-context learning, which is a short way of saying ICL is an abbreviation for in-context learning. And this was a major interpretability observation, kind of that, oh, there are attention heads that are specializing for some sort of coping that then explains in-context learning, which is a core thing that LLMs are doing. And these heads, maybe I won't write it now, are called induction heads when they are doing this kind of, oh, see what was happened before, then check what was the next token, after that one will predict similar to that thing. And in work, follow-up work also by Anthropic, so I'm all the way down. In this work by Olson et al., they basically take these observations from this mathematical framework work about how attention heads can be specializing for doing what's necessary for in-context learning. And I'm trying to make an argument that these induction heads are what drives, it's the mechanism of in-context learning. And that's, it has been a very important observation because if in-context learning is the core thing that LLMs are doing, and we can explain it to interpretability, that's a great achievement for interpretability. Things got a little bit complicated though. After that, there are two works that introduced function vectors, and these function or task vectors were also introduced to explain in-context learning. So they themselves find, ways to say whether certain attention head or not is going to drive the in-context learning. And although this work by Olson et al. Has been, it is when we say induction heads or attention heads and in-context learning, this is the first work it will come to mind of anyone in the field. However, most recent analysis from last year by Kayonin and Jacob have done a very thorough comparison of attention heads and these function vectors. So function vectors versus induction heads. And in long story short, in this work, they have shown that function vectors are those that explain in context learning rather than reduction heads. And there is more to say about this, but I kind of wanted to give you this overview because I do want to teach you what the induction heads are and how we got to them and what are the arguments in a work by Olson et al. But be cautious to, as we are talking about this, kind of remember that at some point I will talk about this comparison, but I will make a point to say that this other methodology that is explained in a different way how in-context learning behavior came about or is functioning in an LLM is actually what this total comparison is saying is a mechanism behind in-context learning. And you can then say, well, why do we even learn about this? Like, what's the point, right? If this is not what drives in-context learning. I think the value of this is it's going to help you read a bunch of papers. So I'm going to introduce something called OV and QK circuits, and people will just write papers and refer to these OV and QK circuits as if you know this background. So there's just a bunch of paper that become readable if you know this, right? And I want you to be able to read those papers. And it's not like this methodology is bad, like useless just because it's not necessarily the mechanism that drives in-context learning as well. So our plan now is to go over this, and then next time we are going to go over these tools. Are there any questions? Okay, then let's get into it. Maybe I will open this one. Okay, so remember this mathematical framework work is the one that we use to derive the residual stream. So when I told you residual stream, basically we have came up to this point, and we did cover that attention heads are independent and additive, but then we didn't cover the rest, right? And this is kind of what we are going to go over today. Okay, let me see whether I'm going to keep this one. This is the next math I'm going to show you will bring us to this point. I don't want to explain this illustration just yet. I will keep it here and then we can refer to it when it becomes handy. Okay. I shouldn't have deleted that. Okay, I just want to give you a little bit of heads up of what we're going to do because I know it's a little bit annoying to just be thrown a bunch of math without knowing what is the purpose, but it's also very hard to explain the purpose without referring some of the math. So I'm going to derive, we are going to go back to the residual stream and I'm going to kind of refactor a few things. And we are going to start with what we call zero-layer transformers, so the toyest of the models one can imagine. Then we are going to talk about one-layer attention-only transformer, no MLPs, no layer normalization. And then I'm going to derive both of these. Then we're going to talk about two-layer attention-only transformer without deriving it. I will just say what would be important to see if we want to write everything on the whiteboard. And through these derivations, we are going to see basically two matrices that we call OV and QK circuits. And when you check these two matrices are going to be squared in the vocabulary size. And by reading these matrices, you can basically see the following. If I was at this token in an input, what would that token attend to? And if it attends to this other token, what would the target, where I started with, what would it predict? Basically, it gives me this kind of read of, oh, if this token attends to this one, which logic would be promoted, right? And then this becomes handy for these things such as coping, kind of to show you. And as an example, if we have those matrices where we can read what I just said, which is really wordy, right? You can see, okay, if I'm at the destination or a target token R, and this token is going to attend to perfect, and if it attends to perfect, the auto token will be perfect. Similarly, if I'm at the destination token contains, it's going to want to attend to the token large, and then if it attends to large, it's going to predict the large. Do you see how if you read this 100 times, you will be like, well, the model, this is just copying, right? And this is, as an interpretability researcher, where you're like, oh, then this attention head serves for copying. Basically, this is how this hypothesis was formed. So the next bunch of math we are going to write all comes to getting these matrices where we can read this information. Okay? So I know it's still pretty vague, but we will get to these matrices and everything. Okay, so as I said, we are going to build our intuition by starting from very toy model and then just complicate it a bit by bit. And the super toy model one can define is a zero layer. I mean, I will write it like this, transformer. Obviously, this is not a transformer, right? So if you have a zero-layer transformer, basically what we have is, it's bizarre to call it a transformer. We have, let's say, a P is going to be our input. So, we are going to write it like this, meaning we have a matrix of the size of the length of the input, so how many tokens I have in the input. If my prompt was ABCD, and context would be just five tokens. But here I have this number of colons to be the size of the vocab, and this is a bit weird, right? This is because I'm representing my input as one hot encoding. So if the vocab index of A is 0, then the first row here would be 1 and all zeros, right? This is the one hot encoding for that first token, right? And I will just stack them row by row. So if the vocab index of B is, I don't know, 2, I would have 0, 0, 1, 2, and so on. Just stacking the rows. Okay. I'm going to have my embedding matrix. It's going to be of the size of the number of words in the tokens in the vocab and the model size. So embedding matrix. And we are going to have unembedding matrix. That's the one we use for producing logits. Okay, and then I'm going to write the same notation. Remember when we introduced residual scheme, we had P of P that were the logits. Is going to be just, first I'm going to take the embeddings of my input, right? So that's just the product of one hot encoding of my input with the embedding matrix. And then I do unembedding matrix. Okay, so now I have logits for every position in the input. I have logits. What would I predict as the next token in that input position? And this is our zero-layer transformer. What is interesting here is this term over here. What this term does, when you think about it, it takes an embedding of a certain token and gives us logits over the vocabulary, right? So it means if I see a word cat, I get information about what the next token could be, right? Those who have taken my NLP class, does this remind you of anything? Like, I have one token and then next token. How do we call two tokens? Jason?
What is it, an engram? Or two?
Engram?
Two-gram?
Okay, 2-gram, which you commonly call bigram, right? So bigram, just in general, engram is a sequence of n consecutive tokens. And we have special words for, we don't say 1 gram, 2 gram, 3 gram, right? Like say one, no, I said it. We will say here bigram, right? For when n equals 2, we say bigram. Okay, so now going back here, I said if I have an embedding of a token, I get the logit, I have logits over the possible next token. In other words, using bigram notation, what is that then calculating? So if I have, okay, I really shouldn't, this is not so important that you say, but I'll keep it this way. So if I have, let's say, embedding cat, and then I have all possible, next tokens in the vocab, and I have logits for each one of these. So I have 5.1, 10.3, 0.1, 0, 0, 0, 0.5. What is effectively, so let's say first one is A. So now, if I have cat A and very high likelihood of 5, what did I basically calculate here? The likelihood of what?
The likelihood of a certain bigram appearing.
Yeah, and here, which one?
In this case, the bigram for cat B has the highest probability of occurring.
Yeah, so if I say, okay, here for every possible token embedding, I get the logit distribution over the next token. Effectively, what I'm calculating is bigram statistics, right? So if the likelihood of A following cat here, I can say bigram cat A is 5, cat B 10. I mean, this is a silly example, it makes no sense, right? So the point here is that the zero-layer transformer is more or less calculating bigram statistics. Okay, now, is that clear? I feel like your faces are like, maybe.
Only bigram or also trigram?
Not a trigram, because we had the trigram when we would need another token here, right? So we would need cat A and then something else, like C after. So it's just like, okay, I think maybe we tried to, so here we have, let's just visualize. We have WE is of the size of the vocab times D model, and then we have D model times V, right? Okay, and we are going to get a huge matrix that's square in the size of the vocab. All right, so let's focus on the first element, so 1, 1 or 0, 0, however you want it. It's a dot product between the first row, right, and the first column over here. And I'm saying this is basically likelihood of a bigram. now here, which bigram? Bigram where we have vocab ID of 1 with vocab ID of 1. So if the word token with the vocab ID is cat, it would be the likelihood of cat, right? If there is a mapping between these two. Okay? So basically I take the embedding of a cat and I make a product with what is again connected with the cat. Here, if we had another, let's say here, we have cat vocab ID of set. By doing the dot product between these two, I would get the background statistic of cat and set. That's kind of the idea here. Okay. I think repeating that won't help much, so if this is unclear, just maybe sit with it at home a little bit. Maybe just working the matrix product yourself can be helpful. But let's continue with one-layer transformer. This is where things get a little bit more interesting, and this is where this coping already emerges. Okay, so now one layer, attention only transformer. No NLPs, no layer normalization. Okay, so again, I'm trying to see what would logics be if I had one layer attention only transformer, right? Here we have, let's call x0 to be the embedding lookup, so the product of one count vectors with the embedding matrix. So I have x0 plus, this is referring to the residual connection, right? So I start with the embeddings, and then I add the output of multiple attention heads in the first layer. I just have a single attention layer. So remember when we derive a residual stream, usually when we teach and learn transformer architecture, you learn that, okay, we have multi-head attention, meaning in a single layer, we have multiple attention heads. All of them, they do their magic and give us a new representation of a token. Then typically we say we concatenate these and we multiply it by a matrix called WO, output matrix, to down project that big vector into something else. And then when I introduced residual stream, I said, okay, we are going to write this differently, but it's the same thing, where instead of doing this concatenate, then multiply, we say, well, just add them independently. And if you don't remember this, it's nicely written in the notes. So, and if you forgot which notes they are, let me know and I can point you to them. So we can write the output of multi-headed attention in layer 1 as hx0, and then all of this is multiplied by wu, our unembedding matrix. Just to repeat, here we have attention only single layer transformer, meaning I have the output of multi-head attention. I have multiple heads, but they are all live in the same layer. I have my residual connection, and then I apply the unembedding matrix to the sum of those. John.
So the assumption here is all the heads are outputting something in linear fashion, I mean contributing linearly.
So this is again we are using a residual stream notation where the output of every sublayer in a more expanded residual stream where we also have MLPs, every output of every sublayer, be it multi-heads attention, be it of NLP is just added back to the residual stream. So here the input, the multi-head attention is X0. We get some output and we add it together with the input, right? That's a residual stream connection. It's just a way of writing things. And here, yes, you are writing this head in an abstract way. You are saying it's just H, right? We are going to expand it here. And usually we take this abstract notation and then everything looks clean, right? Okay, so here we have X0 W U, we have this sum. Now I'm going to expand what this is. Mistake. Let me stop here and then I'll continue writing. So what I did here is I just wrote what A is here, right? So we have A, the product of query and keys. But instead of writing query keys, which are linear projections of the input, I'm going to write it in this expanded way. I want to see the weights. And this is intentional because we are going to read the weights later to see what's going on. So usually when we write attention, we define Q of this head to be X0 times W cube H, and we write query key, right? So as here. And here we are just writing the same thing in a more detailed way, and that's it. Because we want to later look into these weights over here. Okay, so this is A, and then A is always, we have a product with the value matrix, which is a self-linear projection of the input. And then I didn't write it here, all of these would be concatenated and multiplied with WO, which I will bring back here. Okay, so we have X0 WV H. Remember, this is usually just V, but here we are writing everything in this expanded form. And we have WOH, and then WU. Lots to write, right? Okay. Let me write the sizes of these matrices. Let me delete this. So, this one, if this is of the size input length times the model, this is going to be the model times the head. Remember that typically the size of the head is smaller than the size of the model. And typically very often, the head equals the model divided by number of heads. I'll say here the number of heads. So if we had 16 heads, it would be 16 times smaller. Okay, all right, so here we have this transpose, so this is going to be the head times the model. This one will be of the size the model times the head. And WO then needs to be of the head times the model. Okay. The reason why I have written these dimensions out is because now we are going to define something called WQKH. And we are also going to, let me just see whether it's QK or K. QK. Okay. And this one is going to be WOV. commonly see here is that now these are of the size D model times the model. But what is the rank of these? If I have this square matrix produced by the product of these, do we see what the rank is going to be at most?
Okay.
The head, right? So it's going to be of the rank of the head. So we're going to define these, but it's also useful to remember that these are of the way smaller rank than their size. Okay, let me write one more gigantic thing. So this one is going to be, we're just going to say, okay, this is equal to this, W2. Okay. Let me write it down. Okay, here, nothing, the only thing that changed is I introduced that x0 is TWE. Okay, so I replaced it, and then I introduced this new notation here. So instead of having V and O separately, I have OV, and the WOU was there previously. So just to repeat, this part over here, so this thing here is the same as this part over here. Exactly the same, just with written slightly differently. And I introduced a H to refer to this whole thing over here. So I have everything over here is going to be a H. I'm going to write it down. H is the softmax of TWE, because that's what x0 is. I'm going to use this new notation, QKH. WE transpose D. Okay, now with all of that written, we have some very important things to highlight. This term over here, we had minutes ago said what it is. Do we remember?
The Biden statistics.
Background statistics, right? And now we have these other terms over here. So we are going to focus into what each one of these other two is doing. Okay, this one over here is our mechanism that gives us information. Even when you learn transformers for the first time, you know that this one, what is calculated is if I'm at a given token, how much this token want to attend to the previous token that had appeared. The only subtle detail here is that if we look into this part here, WE is of the size of the number of tokens in the vocab times model, right? And this T is one hot that gives me which one of these tokens actually had appeared in the input. But if I ignore these one hot encodings for a moment, and if I just focus on what is squished between them, basically, then what this does is using the same intuition we have about attention as always, it tells me for every possible token, how much some other token will attend to it, just from the weights alone. Okay, so I think what would be helpful here if we just go back and when we do the query key product, how it gives us information about how much one attends to another, and then we're going to come back to this one, which is going to be what we call query key circuit. Just maybe for a moment, I'm going to write almost the same equation, except I'm going to use x0. So now this is of the size of n context times the vocab. No, that's wrong. The model. So this is, I'm afraid that maybe switching back and forth or using this one-hot encoding, you might be a little bit confused. Typically, when we, talk about transformers, we just talk about F0. I say, oh, we have an input tensor. It's a tensor of token embeddings for tokens that appear in input, and I skip this whole business over here. I just say, these are token embeddings, right? So don't forget that, right? This is nothing complicated. These are just our input token embeddings, and a nice way to write that is to define this one-hot encoding and multiply it with the embedding matrix, which is just a mathematical way of writing embedding lookup. You are looking for embedding of each token that appeared in the input. When we have x0 times here, now we have this wqk. But don't forget that wqk is just a fancy way of writing something you know from way before, which is query key transpose, right? It's just a fancy way to write it. Sorry, this is not completely clear. It's not exactly the same. So previously we had query key transpose, but query key transpose is x0 times wq, and then wk transpose x0, right? And then I said, okay, this is going to be wqk, I'm going to define it like that, right? So just try to kind of, I know it's a little bit okay, we are mixing and matching the notation, but I want to emphasize you already know all of this. So when I have my attention mechanism, I'm going to repeat it. I first do my projection, so I have Q is x0 wq, and K is x0 wk. And then I calculate query key transpose. What query key transpose does, it takes every one of these queries, so every row is a query for every token that appear in the input, and we do dot product with every column of our key transpose, which is again associated with everything that's in the input, right? So we are just basically measuring the similarity between two tokens in the input. And then when we have that similarity, right, here the ij element of a query key transpose is how much token at position I attends to position j, to a token at position j. So we know, for example, if this value is 0.9, which is really high, we can say, well, this token at position I attends a lot to the previous token at the position j. And then we use that information when we do the A times B. Basically, we mix all the input representations, which are rows in x0, by these weights that are in a single row. So for row I, which corresponds to token I, we know how much each other token that preceded it is important for it. And then we just mix the representations of tokens correspondingly with A. So remembering all of that, we are doing the same thing here, except if we ignore one-hot encoding, we extend this to every token in the vocab. Instead of just those that occurred in the input, now we are saying for every token in the vocab, if I can see how much token in the vocab would like to attend to other tokens in the vocab from the weights alone. Okay? And this is important to remember. I'm going to delete this and define this whole thing. Is going to be called query key circuit. And query key circuit is a matrix of the size that's a square in the vocab size. Okay, so query key circuit tells us for every token in the vocab how much that token, almost like a priori from the weights, would like to attend to other tokens. And then we have this OV circuit. And we are going to define OV circuit not just to be this OV weight, but rather everything here. So I'm going to write down WV, HWO, HWU. So this one here as well is going to be what we call OV circuit. I'm missing something here, they are all square, and that's because I'm missing WE. This is going to be OV circuit. Unlike QK circuit, that for a given token looks into other token, OV circuit will apply this transformation to every embedding, everything that's in every token. So it's the same transformation. Unlike here, where we are eventually going to transform a token representation based on its individual preferences for the other token. Here, there is nothing relative between token and token. So every token gets the same transformation, right? Using the same, they won't be transformed into the same vector, rather we are using the same mapping to transform it to whatever it's going to transform to. So the way to kind of comprehend OV circuit is, okay, QK circuit tells me which other tokens representation this token wants to attend to, and then looking at that representation, considering also what the other token wants to attend to, now is going to write something into residual stream, and whatever it's written in the residual stream is going to promote certain logics or not. Let's walk through that with an example of coping. With coping, if I'm at a given token, such as perfect, my query key circuit will tell me, well, just from the weights alone, if I'm at the token R, it wants to unchain to perfect. That's what query key will tell me. But then OV will tell me, given that, on the representation, on the residual stream of R, is going to promote perfect as the next token. So I get these two circuits, which then tells me two things, and together they explain how coping can come about. Okay, this has taken way longer than I expected. Let me go over here. So these kinds of analysis with these QK and OV circuits lead to examining with what we call skip trigrams. Trigrams, now everyone knows, are sequences of 3 consecutive tokens, and skip just refers to the fact that we can skip some tokens in between here. So for example, we can look into source destination tokens, so some previous token, some other token where we are examining what the next token would be, and then what the next token is going to be. Here we can have something in between, or there are some tokens in between source and destination, it doesn't matter. To recap, the query key circuit, which is, where is it? Here. It's a matrix that's defined through the product of these three matrices. It's going to answer me given that we're at the current position J, so given a token, given some token, which earlier position, so which other token does this token want to attend to? And then once that position J has been attended to, the OV circuit determines what gets written into the residual stream and which logic to promote through WU. So these matrices, Q, K, and OV, they are both squared in the size of the lookup. And they are what researchers then examine to see whether there are any interesting patterns. Remember when I said these matrices are going to be low rank? This is important also to remember because that gives a hint that although these matrices are huge, so if they have a size of the lookup to be 50,000, the size of these matrices is going to be 2.5 billion entries. So that's a lot of numbers to look at, right? But kind of a researcher who has seen this stat was thinking, okay, but they're all low rank, so there is something, there is less information to actually find here, and that was somewhat the motivation to, or a hope that there's something useful could appear here. They look into these. You can open these yourself. It breaks my laptop because I have too many tabs and windows open, and they're big files. And you can check kind of what these researchers were looking at. Okay. Yeah. So one of the things they have observed is this example I kind of keep bringing up, is that they have observed that the coping behavior where this token is really preferring to look into this other token, and then that token turns out to be promoted as the next token. And then you have some, whatever simple behavior, but here you can also see behaviors that explain why could these LLMs be good at things like understanding LaTeX or HTML. It seems like here these behaviors are already becoming, even a simple mechanism like this can explain why later on the model would be able to do something like writing a LaTeX code or HTML code. There are a little bit more interesting behaviors as well. So, for example, we know that we are not tokenizing words into full words, but rather into subwords. And subwords, when we have these like names, very often they are going to be full words. The tokenizer will learn them to be full words, and they are going to be preceded by white space. But then in text you can have these words appear as a beginning of a paragraph, and they don't have white space. Just do how the tokenizers work, because they are not preceded by another word that won't be this special white space. And that throws off the tokenizer, and it might start doing weird things. But here, the model recovers in a nice way. So it says, oh, I'm at the destination token R. It attends to the full word Ralph, and then it predicts as a next token ALPH, which is necessary together with R to produce the full word. So it kind of uses this simple mechanism to produce the full word from the subwords, which is a nice way to see kind of how the models deal with these tokenization things, even with this simple toy model. Here they just outline different, kind of patterns that have observed, like just pure coping. Here it's not pure coping, it's coping in a sense that you have something that's similar to the word that is being copied. So here 2, and then we predict 3. I wouldn't say call that coping, but it's finding something similar in spirit. Here, instead of perfect, include the sense super, and so on. And already with this simple model, they observed why certain funky behaviors of LLMs can come about. So, for example, here they have destination source token and output token and correct skipgrams that you can produce by predicting the source token or predicting something as a next token to kind of get to whatever the source token was. So PixMap here and QCanvas makes sense, but then the model will sometimes predict PCanvas, which is combination of these two, which is not voided, or here you have similarly to Ralph, trying to predict the full name, and sometimes it works like with Lloyd, but then sometimes it's going to predict C Lloyd or L H-Rim, because it's trying to do the same thing, but it can't do that for certain tokens. So already with this simple stuff, we have observed interesting phenomena and explanations for why certain failures can occur. Now, we have, unfortunately, and I forgot even my watch today, only 5 minutes left, so I'm going to just tell you what to expect next. And for that, I need to recollect my thoughts. Okay, so what we have so far, it still cannot fully explain in-context learning. It is very literal, so it looks at the destination token, which token it's kind of want to attend to, and then based on that source token, it makes the prediction of what the next token is. But we would like to have something like a little bit more contextualized with what's going on in the context. And if we do the same thing we have done here for one layer attention-only transformer, for 2-layer, which I welcome you to do. It's not insane to do, it's just a lot of repetitive stuff, because now we have basically 2-layer transformer takes the output of the 1-layer one and does another layer of attention. So you take all of this plus another one of these sums. So you will get some interesting connection between what's going on in the first layer and the second layer. And one useful thing, especially for in-context learning, is that from 2-layer transformer and this interaction between heads that are in the first layer and the heads that are in the second layer, the first layer can tell the second layer's head that okay, there is this token wants to attend to this source token, but in this particular input, it can also signal what was before or after that token, and especially what was after that token becomes a handy information for the next head. Now, it knows not only, this is the source token and I can copy it, or I can try to see what is, similar word to it or something like that. It can literally use the information of what occurs after it in the given input. And that's way more information than just finding the nearest neighbor to the source token, right? So it's more information, and then this information, this capability is what this set of authors are claiming that can explain in-context learning, but then remember the comparison that I mentioned. So next time, we are going to, I will not derive this to a 2-layer attention-only transformer, because if anything, I realize it's too slow. But I do welcome you to do it. I will warn you that the way they derive math is using a different notation. So here they're using these tensor products. They claim it's a little bit more intuitive. I don't find it more intuitive, so I was sticking with just a normal matrix vector multiplication. So I If you want to do it the way I did it, I don't recommend going back to this work and trying to follow what they are doing. If you want to try it, there is nothing to it but just recognizing that this is an input to the next layer. So you write even more complicated equation, and then, as I did, you just continue expanding and expanding it, and eventually you will get these three terms. You won't get exactly the way they have done it. Let me just find it real quickly. Layer. Okay, so if you do it, you will get three terms. They won't look exactly like this because if you're not using tensor product, you won't get the same thing. But whatever you get, these three terms should correspond what they are describing here. So I welcome you to do that. And next time I will just briefly say what if we were to do it, what we would get. Then we are going to define these induction heads and talk about this, how this work had claimed that induction heads, which kind of experiments and arguments had suggested that induction heads driving context learning. But then we are going to switch to function vectors and talk about the comparison and kind of learn that maybe function vectors, if you want to investigate similar kind of attention heads for whatever you want to do, function vectors might be a better choice. Okay, let's stop here. If you have any questions about projects, please